Hello, everybody. Welcome to video 5, which is portion of chapter 18. I'm going to pull up the PowerPoint slides and we will get started. So if we go right here to chapter 18. Now, remember, the regression model and the ANOVA model are portions of the general linear model. And the really major difference that we've seen between a simple linear regression and the analysis variance model is in the simple linear regression, usually the predictor X is a continuous quantity. Whereas in a ANOVA model, we've seen that the predictor X is a categorical variable, such as treatment condition. So, but with both of them being based in the general linear model, the assumptions of the model remains either the same or really similar, or just requires a little tweaking to fit the ANOVA model. Nonetheless, just think of the regression. The ANOVA model is really a special case of the regression, which you can fit through dummy coding, dummy variable. But so basically the techniques you learned in 5.12 will carry over here with a lot of the components of the goodness fit. The first one being focusing on the residuals. Now the residuals, losing my symbology here, but namely it's the residuals, again, think of it alphabetically. It's the observed quantity minus, this should be predicted, it should be a hat on top of this. I lost the math type symbol switching computers. But again, verbally, the residual. So again, the residual for the jth person in the ith level, again, that's our ij subscript, is the observed value for that data point minus the predicted. Or in this case, for the ANOVA model, it's the observed minus the cell mean. What is the mean of that respective level? Now, this will having the residuals will help us assess one of the assumptions models, namely whether or not the residuals are normally distributed. Because again, we're assuming the residuals are IID, independent and identically distributed, with a normal distribution mean 0 and some common variance. The variance is estimated by the MSE. So the normality of the residuals is one of the assumptions that we will need to check. One of the other goodness of fit things is getting after whether or not we have outliers. And again, remember, an outlier is an unusual, a unusual predicted value that's either much larger than you would expect, or I guess really an observed value that's much larger than you would predict, or much smaller than you would predict. And to really get these outliers, one of the things you saw in 5.12 that was really helpful is getting the residualized or standardized residuals. There's a bunch of different forms of the standardized residuals, but if you guys remember from 5.12, the jackknife residuals, which are really the standardized residuals excluding that observation, seem to be the most robust as far as identifying residuals. So that becomes really one of the big components we want to use at our availability to identify them. In 5.12, a couple of the goodness of fit plots you performed was to look at the data and look at the data as a function of the predictor. So in this case here, it's basically the original plot we were doing, where we end up having the scatter plot on the x-axis, the level of the data, on the y-axis, the outcome. And we were basically doing that for two parts. One, to see, okay, how do the means look like they appear to vary on average, as well as looking to see if we saw that homogeneity of variance. This could also be helpful in assessing any kind of outliers that we want to do. But for us, the explanatory variable, the residuals in the ANOVA model, they're not going to be really as informative as a regression model, just because the levels of the predictor are the respective categories of the variable in the class statement. So you're not going to exactly have the spread that we saw before, but it'd be a good way to assess, potentially outliers. Another plot that's going to be really helpful is the residuals versus the observation number or time. One of the assumptions of models is independence. And sometimes in studies, how the data is acquired, maybe time-wise, can create some kind of internal correlation, or what you may have verbed in 512, this autocorrelation. And I always give it the sense of like a depression study. And a lot of the depression study data that I've been involved in, you guys have seen some of the depression study data that I've been involved in already. One of the things we get is these people are recruited over time. And as silly as it may seem, there are a lot of times are these seasonal trends. And what I mean by that is you could have somebody where it's okay, you get them in January. The holiday season has just come, that credit card bill from the holiday season arrives, and they're depressed because of the bills they have to pay for the previous holiday season. Come to February, get to Valentine's Day, love's in the air, people start getting really excited, they get a little happy, depression's less, they improve. Then you get to into March where you start realizing, all the chocolate you ate at Valentine's Day, you get more depressed. And then you start getting, after March, you start seeing, hey, little spring is in the air, the flowers are starting to bloom, less depressed. Then you start realizing when you start getting into May, Memorial season, a guy not in shape that much for beach season or whatever, more depressed. Then you get into June, you're happy because the kids, or maybe not for some people, you're happy the kids are out of school, less depressed, more excited. Get to July, you start realizing it's really darn hot. So you're getting more depressed again. You get to August, you realize, hey, start of football season, get more excited. September, depressed because school's back in session. October, excited for Halloween. November, you're depressed because of, you're going to see family. Thanksgiving holidays you don't really like. And then you get the holiday season, December, you're all excited, less depressed, and all enthused. But that's, you have that little bit of a zigzag going on. We call that pattern, we also call that pattern a sawtooth pattern, because you're going up, down, up, down, up, down. Statistically, that's called a negative autocorrelation. So namely, as the data points come in, there is an internal relationship of that data. That makes the data not independent. It violates the independence. So having a sense of what's going on with the residuals over time can help us visualize that. Big one, standardized residuals give us a sense of outliers, and then the normal quantile plot give us a sense of the normality of the residuals. We're going to see these plots in three ways. We're going to see the auto plot by proc GLM as one way to do it. We'll show a couple of the plots with SG plots, or SG, the SG plot mechanism. We'll also show the in SAS, or the proc SG plot, and we'll also show them with proc G plot as we start moving on. So the big thing we have to think about is whether or not we have a constancy of the error variance. In regression, that was homoscedasticity. In ANOVA, we're going to call that homogeneity of variance. The other one we have to think about is the non-independence of the error terms. So this issue of autocorrelation may be something we need to inspect for. Outliers, the emission important predictors, that's not really what we're doing yet, but as we extend the general linear model beyond ANOVA, will be something to keep in mind of whether or not we need to have some control variables to help explain what's going on is something we may have to keep in mind. And then the last one is non-normality of the error terms. Now, in 512, you handled those two as well as this possibly by using transformations. We're going to see in the ANOVA model, the outliers and the non-normality of the error terms, we're going to handle by transformations. The non-constancy of the error variance, which is a violation of homogeneity variance, we're going to handle it by modeling the fact that the variances are unequal. So the ANOVA model allows us that flexibility. And the benefit of that is we keep the outcome on the original scale. One of the biggest problems with transformations is that the outcome is transformed. And then instead of talking about a on average effect for a unit change on the outcome, the units are different. Instead of say dollars, it's square root dollars. And sometimes that becomes a little hard for the person whose data you're analyzing to comprehend. And like we said before, and like we said a lot, you know, statistics is communication. And we're got to tell the story that the investigator understands. So the non-constancy of the error term. The first thing we're going to look at is look at this plot of the residuals versus the level of factor for a large study uses a standardized residual, look for similar power across the factor. This test of constant variance. And we're going to go ahead and take a look at this chapter 17, 735 program. So we go ahead and pull that up. I got a different one up. So if you guys remember with this, I call it chapter 735 diagnostics. This is our rust inhibitor data. So let me go ahead and just get the data loaded. And then after the data is loaded, let's just go ahead and take a look at the thing. Now with the diagnostics plots, a couple of things to point out in line 64. The plots equal all on that proc line is going to create a lot of the automatic diagnostic plots that we may find useful. Line 67, you can see here, I'm creating a data set that's going to contain a variable, the resid, which are the residuals. P hat, again, remember, the info just augments the rust data set to have additional columns where we have a column called resid, which is, again, the residual, observed minus predicted. P hat, the predicted value. STD res for standardized residual, and then jack res for the jackknife residual. So again, the student gives us the standardized residuals. Again, the residual on a standard Z scale. And then the R student does the jackknife residuals. So we got this all out. So let's go ahead and do, if you don't have the graphics on, line 62 turns the graphics on in SAS. And again, if for some reason you had the graphics off, I have it on, that would automatically turn it on. Again, I said to you guys before, a lot of times in my output, I turn the HTML component on and off, depending on how much output I'm kicking out. So we ran this before, and we knew there was an overall effect, right? And that was, you know, part of the output of the rust inhibitor data. But let me go to the beginning. So as we saw with the rust inhibitor data, based on the available data, we have sufficient evidence in our data to indicate that the on average mean protection of these 4 brands of inhibitors are not the same. And that way statistical evidence indicated that at least one is statistically separating from the others, right? We knew that. And again, remember, this is the estimated variance between the cell means and the pooled variance within the cell means right there. So now this is our MSE. This is our estimate of sigma squared. Again, you know, we saw this R squared. It's crazy huge how big this is. So now this is the predicted value versus the residuals, right? This is a pretty good plot, right? So now we can look at this and go, okay, three things, I guess, a couple of things we could see really quick here is now, do we see whether or not the spread of the observation seems pretty reasonable, and pretty similar across the 4 levels of the predicted values, right? So these represent the x-axis represents the on average mean for the 4 levels of brand, right? So we see 2 of the brands are pretty close with their rust inhibitor grading. Got that one, we got the best right there, which I believe is brand 2. So we see that, so look at the spread. It doesn't really look like anything crazy. It looks like, we got pretty similar spread of the observations around the 4 brands. Next thing we look at is, do you see any really outliers, things that separate from the pack? Now you got to look vertically. Right? And maybe this one, not really. Go down to predict the second ordered predictive value. It doesn't really look like a lot of things are super spread out. So do I expect any kind of violation of, any kind of outliers? And do I expect any kind of violation of homogeneity of variance? Not from this upper left-hand plot. This starts giving us the jackknife, our students, the jackknife residuals as a function of the predicted values. So in 512, you may came up with these rules of thumb. A couple of the rules of thumb are that you had was, okay, if a standardized, or in this case, jackknife residual, was bigger in absolute value than 3, that was definitely an outlier. If it was bigger than 2.5, that's when you'd investigate it, and when you be suspicious whether or not it's an outlier. And when it's bigger than 2, then you're really worried this is an outlier. Or I guess more questionable it's an outlier. So again, the 3 rules of thumb: 2, it's questionable; 2.5, you're worried; 3, it definitely is. So we could see in this case, here's -2, here's 2. We may want to look at these 2 observations. And now remember, when you're dealing with outliers or potential outliers, the 2 things that you have to keep in mind, the 2 questions you have to keep in mind is, 1, ask yourself, why is it possibly a believable response? And 2, why is it unusual? The 2 questions may seem to be interrelated, but the first one, is it a reasonable response? So again, if you're looking at, okay, well, like a test score, and you go, okay, well, if the data point's 110, it's not a reasonable response unless there was extra credit or something like that. If you're talking something on a 0 to 100 scale, not a reasonable. It's got to be a typo, some kind of mistake. Instead of 110, it's 100. So first, is it a possible reasonable response? Then the second one is to ask why is it so unusual? Right? And some of the unusuality could be something as simple as a data entry error. Somehow they missed a decimal. Somehow, instead of entering 28, they entered 82. Right? And a lot of people do this, just clumsy on the keyboard. We're all guilty of it. Especially if people are entering these things on the phone. How many times you can send a text and spell check changes it into something that you totally didn't mean at all. So again, again, let's go ahead and you have to go ahead and ask these issues when you start getting to the data. So again, we would take a look at those as possible outliers. The next one, the next 2, I'm gonna go down this way, and we'll go down, straight down. These 2 right here, let me scroll these down. These a lot of times can give a sense of whether or not an observation is potentially influential. And I don't know how deep you guys got into this 512, but an influential observation in a regression model can pull the regression line a little bit more dramatically than the other data points. The ANOVA model would kind of run a little similar. Could be pulling the cell mean a little more than some of the some of the other observations. Be something like, okay, you got 4 modes of education, and on the third mode, the third mode of education, you got, okay, the students in that mode of education got score 48, 42, 41, and a 92. And 92 is going to really drive that cell mean. Got these rules of thumb. So again, you would look to see these observations that have these unusual as potential goodness of fit issues. So again, it gives us this rule of thumb, which is pretty good. Here is the predicted value as a function of the rating. Again, so you could look at this as possibly eyeballing any kind of homogeneity of variance issue. The spread of the observation just doesn't look that bad. Slide over this plot right here. This is the normal probability plot, or sometimes called the quantile plot, which is a function of the residual over the normalized residual. Now, this plot is you saw in 512. This plot has a lot of snaking, right? Usually snakes a lot, especially at the 2 ends of the shape. Now, the closer that the dots are to that line, indicate the more normal the residuals are. When it starts deviating from the line, we start seeing deviations in normality. But now remember, our whole goodness of fit assumes, we're trying to eyeball whether or not the residuals are approximately normal. So, one of the problems with a lot of the plots are they're all visual. They're all visual. It'd be really good to get a quantitative feel to the plot besides a visual. Because one thing with the visuals, they're all subjective. So again, people can say, does that appear to be a line? I would look here. Yeah, that looks approximately, approximate normality of the residuals. So these snakes look pretty, that snake in dots look pretty linear. Again, this isn't a line you want to walk a Friday night after happy hour. So again, you have to keep in mind, we have to find a way to kind of get a sense of a test, a quantitative assessment of the normality of the residuals to couple with the graphics. Down here below, again, this is giving us a histogram of the residuals. And again, one thing with a lot of the graphs you have to keep in mind, we don't have a lot of data in this sense. And one thing you guys are going to see with the graphs, the diagnostics get really, when you don't have a lot of data, things aren't going to fit textbookish with respect to normality. The counterpart to this, when you have a lot of data, then the plots get really thick and really busy. So you have to keep that balancing act. The last one is just again showing you, the fitted means and the residuals. It's basic, almost kind of like a little linear facet to this one's really not so much goodness of fit, but more a display of the spread of the residuals. It's a function of proportion less or not. And then this is just the information of the model, which is unbelievably huge. Like I said to you guys before, I've never seen an R squared of 98.6 in real data. This starts breaking out our output from the model. So again, the box plot. So I prefer the scatter plot because you see all the dots with the mean profile line we've done before. These are probably the 2 suspicious observations that we're looking at. Our cell mean. So obviously brand 2 was the one that really jumped out. It was brand 1 and brand 4, which are pretty comparable. And like we said, that is like a shark fin. So anybody's a fan of Shark Week, here's a shark right there, or I guess it was Shark Fest they called it. They call it now instead of Shark Week. And without the sci-fi shark and Sharknadoes, I don't know how much of a festival it is. So we got that right there. Here's a couple of the plots. I'll show you guys a G plot. Remember, G plot's a little clunky with some of its plots, but again, I'm giving you guys a couple templates that you can massage through your data as needed. So again, the G plot with our, the raw data, not the mean profile line. The residuals as a function of brand with the G plot. Again, with this one, I don't see any violation of homogeneity variance. The one thing with the plots is if there's a violation of the assumptions, it's got to be there. You got to see it. You could stare at a lot of these plots and see a mirage, see something that's not there. But the big thing is, a glaring issue should pop right out. Let me show you guys this one really quick. Right, so that's our plot right there. Let me just do one more. I'm just going to copy this really quick. And I'll go. Thought I had this set before, but I guess I did not. So in this case here, I'm going to sort the data by brand and unit. So suppose in this case, suppose the ratings were sequential. So the units that we see in the data point, I go back up to where the data was. So these 10 ratings were on sequential days. And suppose the sequential days were painted during the summer or whatever. The temperature of the day has an impact on the quality of the paint. So possibly if we think of these as days or maybe even months, the durability of paint usually depends on when you apply it and even the time of day you apply it. You can see a lot of times when people paint in the heat of the day, the paint bubbles and it doesn't create that locked effect of stuff. I'm talking like when you're painting outdoors. Obviously with the rust inhibitor, you're not doing it indoors. At least I wouldn't think you would. But again, that keep that in mind. So I'm going to sort this data. Now, going back to data, I'm going to assume within brand, the 10 observations are sequential. Sequential days. So brand 2, sequential days. So within brand, I'm worried if there's autocorrelation. Possibly maybe the resilience of the rating may be dependent on, the order. So therefore, possibly violating that independence assumption. Here I'm going to look at it visually. And I'm going to change it one more time. Go and change this one more time. Save this. So if I go here, here are the 4 brands. All right. So now, one of the things we worry about is whether or not there's autocorrelation. There's 2 types of autocorrelation. What we call positive autocorrelation and one we call negative autocorrelation. A positive autocorrelation could be one where you see the residuals consistently go up as brand increases. actually, I'm going to change this plot. That shouldn't be brand. That should be unit. So we'll make that quick change. And I'll save this for you guys so you see the final copy. So this is unit. Right? So one autocorrelation is positive autocorrelation, which be when the residuals consistently either go up across the units or go down across the units. Right? That's positive autocorrelation, because again, it's basically saying that the residuals are following a linear pattern. They're either consistently going up or consistently going down across the units. The negative autocorrelation is that sawtooth behavior, where we see residual high, low, high, low. Here we get a break of it. Well, I guess it goes a little high, then low, low, high, low. So I'm not thinking that there's necessarily a significant autocorrelation within brand 1. We go brand 2. Almost looks like we've got this sawtooth pattern here, except this and this break the string. Think about it. Without this dot and without this dot, it'd be down, up, down, up, down, up, down. That would be a sawtooth pattern. That would be negative autocorrelation. One's up, next one's down. Next one's up, next one's down. Next one's up, next one's down. But with these two data points here, we break that streak. So again, I'm not sure. We go here, it's kind of almost similar. We have this data point and this data point break the streak. Without those data points, we go up, down, up, down, up, down, up. But these two break that streak. So again, we're seeing a little bit of a sawtooth pattern. I don't know if it's enough. Then here, it doesn't really look like it's as bad. Because again, we go up, down, up, down. This breaks the streak. Up, up, down, up, down. So it's going to be kind of curious to see if we got it. But the one problem with the graph, it's all visual. It's all visual. It's all subjective. We need to get some sense of a quantitative attack on this. And the one way to get to a quantitative attack on this is to perform a test. So for the test of independence or violation independence, we're going to do this. So you're going to, okay, well, you're using proc reg. I'm only using proc reg for this goodness of fit test with independence. So again, you guys may have seen this in 512. And maybe even the time series class, if you guys, those guys took that elective over the summer. I believe it was this past summer that went on. But the big thing is, we're looking at line 127. And with line 127, there's these two components, DW and DW prob. Now remember, we said we were looking at whether or not there was autocorrelation within brand. So the big thing with the autocorrelation and the possible violation of possible violation of independence is somebody's got to say to you that there is some kind of sense of ordering of the data, where you need to see whether or not, whether or not the data is possibly, autocorrelated, therefore violating independence. So, in the depression study, I said, the patient numbers are assigned in how they were randomized. So the patients were ordered. So I can see, is there this kind of timing trend that can affect autocorrelation? In this example, we said, okay, within brand, the ordering of the units follows some kind of time or daily sequence. So I'm going to do this proc reg by brand. Now the models, I'm using resid as a function of the ordering variable. The ordering variable in this case is unit. Now I don't care anything about the output of that proc reg except for the output being generated by DW, the Durbin-Watson statistic, and DW prob, which gives us the most important, the p-value of the Durbin-Watson statistic. Let me go ahead and run this through and show you guys this. So when I go here, well, it'll take a little while of the output. I don't care about any of this output. I'm going to go to the very top of the output. There's brand 3, brand 2, brand 1. Don't care anything about this, except for, I hopped over it too quick, except for this part right here. This is giving us the Durbin-Watson test. This is giving us an estimate of the autocorrelation within brand 1. It's negative. Right? This, now keep the note. So PR less than DW is the p-value for testing positive autocorrelation, and PR greater than W is the p-value for testing negative autocorrelation. So we got the two p-values. We can see here in this case, neither are significant. So based on the available data, we do not have sufficient evidence to indicate significant autocorrelation within brand 1. Jump down to brand 2. Do the same thing. Again, I don't care anything about any of this output till right here. Here's the estimate of the autocorrelation. It's a little bigger. Now remember, these autocorrelations are correlation coefficients. So they range from -1 to 1. But what we again see is here are the two p-values. Based on the available data, we do not have sufficient evidence in our data indicate a significant autocorrelation within brand 2. Drop down again. Again, don't care anything about any of this till there. So now, in this case here, we could see, again, here's our estimate of the autocorrelation within brand 3. Here's the p-value. So again, we see based on the available data, we do not have sufficient evidence in our data indicate a significant autocorrelation within brand 3. So no evidence of significant autocorrelation within brand 3. And then we drop here, brand 4. Again, here's the autocorrelation, here's the p-value. So based on available data, we do not have sufficient evidence in our data in case it's going to be an autocorrelation within brand 4. And that's the end. So cool. So cool, that gave us that. Let me jump back to our notes, right? So the independence. We need some sense of an ordering variable or ordering pattern. All right, so let me go ahead and we'll flag this real quick. All right, so we need some sense of an ordering variable, ordering pattern for the residuals, which could create this autocorrelation. So our Rust inhibitor data. We saw an ordering. Then brand. Graph the residuals. As a function of unit. look for a pattern. The over the units. So the residual is constantly going up or going down over the units can indicate positive autocorrelation. And then the residuals. Going up, down, up, down. I don't want to do things in the movie. See if this gives us anything. So we go here real quick. Get back to our notes. Right, so again, if we go here, what I mean by sawtooth, we zoom in. You can see, and it's a little hard to see, but basically the blades go up, down, up, down, up, down, up, down, up, down. The little teeth on the saw. It's kind of what we see going on. So that's what we mean by sawtooth. So this up, down, zigzag that you see going on. So those residuals going up, down, or down, up, could indicate negative autocorrelation. The big thing is so again, we use the Durbin-Watson test to statistically assess whether or not we have a violation or not. So that's cool. That's cool that we got. So we saw no evidence of a violation of independence in this case. But now here's the big question. Here's the big question. Again, we have no significant effect. We assume that we have no evidence of a violation of independence. Man, you think the spelling would help me out, and but I feel like Dan Quayle. Independence. Independence. Thank you. Independence. Okay, cool. So we know violation of independence, therefore we assume the data are in fact independent. Big question is, what if we have a violation? What if we have significant autocorrelation detected? No transformation So this is the big thing. If we do have a violation, no transformation can correct this violation of independence. Therefore, we just say it's a limitation of our analysis. And any results produced by this model should be interpreted with caution. The big thing is you violated one of the assumptions of the model. If you violate one of the assumptions of the model, the results can't be interpreted. You know, it's almost that, you know, you're not modeling the data, right? You're throwing the data in a model that's not built for it, right? So again, you know, as statisticians, our job is to model the data, not throw the data in the model. Now, I know one of the things with the program that we do is we're exposing you guys, here's the topic, here's the model for that topic. Here's a topic, here's the model for that topic. You know, so education-wise, we're data, throw it into this model. Data, throw it into this model. This kind of data, throw it into this model. Whether you guys are seeing this 513 this fall, or is additionally with 507 when you're dealing with categorical data. The big thing is we have to model the data, not throw the data into the model. And if our data violates one of the assumptions of the model, it's a mismatch. They don't go together. So we got to be very cautious with respect to that. So again, keep that in mind as we move forward with that. So again, so we see that. Let's get back to the program. This one's looking at the normal probability plot. You know, the auto plot does a really nice job. I'll show you guys the code to do it in SAS. It's going to create with respect to the Gplot output. Again, I'll go to this window. Now, it's the same plot we saw in the auto plot. And again, I don't think it's deviating from normality, but again, this is subjective. This is subjective. And when it's subjective, you know, can we get a sense of what's going on? This one here, going to give you 95% confidence bounds of the residual. Again, the residual is versus the unit. I could have did this up above, even though I did it here. Here's a look at the outliers, right? So here I'm using, now this is important. To get a sense of normality, here's a test of normality. Whether we're looking at the residuals or the jackknife residuals, I do the normality test on the residuals, not any kind of standardized residuals, even though the jackknife aren't exactly the same as standardizing the whole sample. But with the normality test, we'll get this through the Shapiro-Wilks. In this case, in the proc univariate, if you throw normal it will give us the normality test. When I go here, I'll jump up to where we're at resid. This is giving us the normality test. SAS is going to produce 4 in this normality test: the Shapiro-Wilks, Komorov-Smirnov, Kramer von Miss, and then the Anderson-Darling. These 2 seem to be the most popular, the Shapiro-Wilks and Komorov-Smirnov. The Shapiro-Wilks was a little bit more, initially it was a little bit more stable for small sample size, and the Komorov-Smirnov was better for big sample size. SAS and a lot of the other software packages have created this to where both of them are stable for any sample size. With the Shapiro-Wilks, it kicks out a statistic W, right? So with W, the proximity to 1, indicates more normality. The Komorov-Smirnov, it's, really comes to proximity to 0.1 and even smaller, that indicate approximate normality. These 2 produce p-values. The p-values here. So kind of like what we saw with the homogeneity of variance test. These tests have the assumption that the residuals are normal. And the p-value is based on so based on, so the assumption is based on the available data, the residuals are normal. The residuals are normal, as opposed to the alternative, the residuals deviate from normality. So with us, we're looking to see whether or not, whether or not there is a significant deviation in normality, to be a problem. So in this case here, with the normality test, if we go back to here, the normality test, we go back to these normality tests. So again, the visuals are subjective. So again, when you're doing the test, on the on the residuals, we'll add this out here, down here. So we're testing on the residuals. Now test on the resid, not the standardized. So again, you can look at things like histograms of the residuals, the normal probability plot, the test. Shapiro-Wilks test. So again, we go back to the output. So let me just steal this. So the Shapiro-Wilks, Komorov-Smirnov seem to be the 2 most common that we end up dealing with as we start moving forward. So those 2 seem to be the most important, So remember, with these tests, So remember, in this case here, null normality is met, alternative normality is violated. So we got to keep in these situations, right? So this is almost like Levine's test of homogeneity variance. So again, you know, if they're not significant, we would say something like no evidence in our data that normality of the residual is violated. Therefore, we will assume the normality assumptions met in our data. So that really becomes what we do analytically. So now you guys can see there are these, you know, the two most common tests and the other two. Which one do you use? I usually lean to Shapiro-Wilks, but what really determines this is your SAP or your DAMP or your SOP. And you guys might be saying, well, what are those initials? Usually in any kind of analytical area you're working at, you have these guidance called the Statistical Analysis Plan. That's the SAP. Or the Data Analysis Management Plan, the DAMP, the DAMP. Or your SOP, the Statistical, the Statistical Operating Procedures. Or whatever people call it wherever you work or could work in the future. In that, they lay out usually the common techniques. So in assessment of normality, we will use the Komor-Smirnov. In assessment of normality for model fitting, we will use the Shapiro-Wilks. The big one is to make that choice a priori before you analyze the data and not let the p-values determine your choice. Now, if you let the p-values determine your choice, it's kind of cheating. You know, it's kind of, you know, seeing the future before what you got, and you know that's not right. It's not right. You know, so again, analytically, guys say, you know, a priori, I'll use the Komor-Smirnov to assess my normality of residuals in my linear models, and blah 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 like that. So again, that becomes really the big important component you guys should think about. This one, I'm giving you a chart of the jackknife residuals. All right, so again, you can see in this case here, we got the big one back here on the borderline back here. And what you can see I'm doing right now is I'm printing out where the absolute value of the jackknife residual is greater than 2. So I got these two observations. So you can see in this one, brand 1, unit 6, they have a rating of 47.7, which gives a residual of 4.56. So their residual is 4.56 above what their observed value is, 4.56 above their group average. Similarly, observation 32, unit 2 and brand 1, their ratings 45.2, which is 4.73 units above their group average. So these are ones we may suspect. Now, like I said to you before, it's kind of like, okay, well, these two scores, are they believable? Yeah, they're believable scores of the rating. No, it's nothing that looks out of range. But then the next thing is, you know, are the data legitimate? And if the data is legitimate, you know, it sticks. You know, the big thing is we see them, we fit the model. Now, when you have outliers, you know, especially in the ANOVA model, when you have outliers, that usually creates bigger variance. And the bigger variance usually creates bigger standard errors. So a lot of times you have less chance of rejecting the null. In a regression model, the outliers can really move the regression line. With the ANOVA, it's not as much since we have multiple observations within each level of the predictor. So usually they increase the error. So that becomes the big component of the ANOVA model. But I would look at these two jackknife residuals. Okay, they're just above 2. So if these values are legitimate, they stay. Now remember, when you analyze data, this is also got to be part of the data analysis management plan, or how you're going to handle outliers. My rules are you never throw away data. If the only time you throw away data is when the data is not accurate, right? So again, if the rating scale was on a scale from 0 to 100, and this was 147.7, my steps would be 2 things. Can you fix the data? Then if you can't fix data, it's removed. Because data is not accurate. It's not reliable. But in that case, this data is legitimate. If the data is legitimate, it stays in the model. If the data is not legitimate, that's when you remove it from the model. So this becomes a really big thing. And usually it's not us making that decision. It's usually us in conversation with the investigator. Going, hey, we have a couple questionable data values. Can you help us do data quality checks? In the olden days, when a lot of the data were hand entered by people from surveys, data errors were common. In the data transcription, a lot of times when people are entering things on iPads or even iPhones or any kind of smartphone, the data entry isn't as much of an issue unless you're dealing with a bunch of clumsy typing that you can run into. But this becomes really a big thing that we really need the investigator and the investigator's team, the person who owns the data. What I mean by the investigator, to really help us walk through a lot of this. So this becomes really important component. Next, we get into the quantity of variance, but let's jump to our notes really quick that we were looking at this. So with the normality, in this case, bring transformations model to help us correct the violation. So again, we would do that with the outliers, like we said before. This requires communication with the investigator. Talk about whether or not some values are actually truly legitimate and all. And again, with the outliers, so again, when we have an outlier, The big thing is we've talked to the data people, the people who acquired the data, whether or not the data value is valid. The only time we throw away data is when the data is inaccurate, when the data is not valid. We don't throw away data blindly, right? So if the outlier is a true data value, we need a model that accommodates and models it. So again, if our data is kind of, again, it goes to modeling the data and not throwing the data into the model. For me, data costs money. One study I'm involved in looks at acute respiratory distress syndrome, what we call ARDS. And in this ARDS, the thing we look at is we look at any kind of like biomarker measures that can predict the onset of ARDS. And the ARDS isn't linked to the COVID issue, even though it talks about lung function. It's ARDS is usually linked to people on respirators, which could be some of the COVID people, but the study I'm involved in deals with people who suffer some kind of trauma and they're put on respirators. When they're on these respirators, if this ARDS develops in their lungs, it's highly, high mortality rate. The biomarkers we get on the individuals is, we usually get a lot of different blood and urine battery measures, and a daily cost on the complete biomarker assessment on an individual is about, I guess about 10 years ago when, the heart of the project was going. It might be cheaper now, but 10 years ago, the battery was about like $8,000, something really obnoxious per person. And they would do this, daily. They'd do this daily for a month on an individual. Now, the good news in a weird way for that was this ARDS, it was highly high mortality rate, so not everybody lasted the 30 days. So if you want to talk good news as far as cost, that's good news. Obviously, people dying is not a good news. But the big thing is, couldn't just throw away data there. I'm throwing away data, I'm throwing away money. Some of the data you guys look at in the textbook, okay, this is kind of goofy data, the Kenton data, not necessarily money involved in that. But, remember, data is money. So the investigator, it's kind of like, you got to be very cautious about what you're throwing away blindly. So we have to keep that in mind as we move forward. This starts giving us a look at homogeneity of variance. So if you guys remember, in SAS, line 2, 54, 55, and 56 are doing a homogeneity of variance test. So like we saw before, when we get back to our notes, so this homogeneity of variance test, what I got there, I got yellow, so I'll make this. So if I go here, make that guy green. Right, this guy goes with the blue. Okay, so with the homogeneity of variance test. Mean statement's going to do the formal test for us, right? So again, with the visuals, we've already seen this, looking at the spread of the observations or the residuals around as a function of the category or the predicted value. So again, our original our original mean profile plot with the raw data overlaid. The mean statement will do this. Again, remember what we said before. The null was equal variance was met. And then the alternative is a violation of the equal variance assumption. So we got that. The visuals were good. But the means test, we're going to go ahead and do these tests here. So if we do these tests here, if I get back to the code, here's the HOV. HOV test equal BF. There's other forms of the homogeneity variance test. Line 254 is going to do the Levine's test. It's the default. It's actually the one we want. The Brown's, Forsyth, and the O'Brien are refinements of the Levine's test, and they refine for allowing deviations of normality of the observations. If the observations deviate normality, we wouldn't be doing an ANOVA model. So again, the Levine's test is the one we want. When I run this, let's go ahead and take a look at this. Okay, we already know the results, and we'll go up to the top of the output. Here we go, at the top of the output. Here's the output from the Levine's test. So Levine's test, so as you guys see there, there's the p-value. So based on the available data, I do not have sufficient evidence or data to indicate that the variances are unequal across the 4 groups. Therefore, I will assume the homogeneity variance assumption is met. So a lot of this goodness of fit, we're kind of accepting the null in a sense. Here's the output from the Brown's, Forsyth. So allowing deviations of normality, it's using group medians instead. Yeah, if we have a deviation of normality, we'd either fix it with the transformation, or we get rid of it in this case. So in this case here, based on available data, we do not have sufficient evidence in our data to indicate that the variances are equal. Therefore, we'll assume the homogeneity variance assumption is met. And then this is the last one. So all of them are variations. The p-values all, again, you don't play the p-value game, right? You stick with one approach, and that's what you do. Again, I'd recommend we use the Levine's test. Again, you guys get out there in the field, your statistical analysis plan may say something different. Usually the 3 approaches run pretty close to each other. Always depends if you're dealing with one that's close to the fence. But that really helped. Now remember, the homogeneity variance is nothing more, is the same thing as what you guys saw with homoscedasticity. I'm going to show you guys this quick example from our book, which is looking at age and diastolic blood pressure. So let me go ahead and load this data up really quick. In this case here, we're using diastolic blood pressure to predict age. And so when I get here, I'm going to go ahead and do the plots. So when we start getting to the plots here, here's the predicted value as a function of the residuals. And if you guys notice in this plot, it does look like there's a little, what you guys call in 512, that funneling out. Funneling out's evident even if you look at the standardized residual. No issues with normality. Maybe a couple outliers we look at, but normality doesn't look that bad, but it looks like we have a little funneling out. Highly significant relationship, R squared of 0.4, right? So you're talking about, probably a correlation of 0.62 or something like that. So a really strong relationship between age and diastolic blood pressure, but we see this funneling out. Now, you guys may look at that and go, okay, I see a violation of homoscedasticity. Then some of you guys may look at that going, I don't see a violation of homoscedasticity. Then some of you guys may be looking at that going, what are you looking at? Either way, any way, it's kind of, it's totally subjective. can we get a way to quantitatively assess violation of homogeneity of variance, or in this case, violation of homoscedasticity? With the homogeneity of variance, we got the Levine's test and the variations to help us out. Do we got anything similar with the regression model? And the answer is yes. And one of the things I do in this case is in our data set, you guys see line 330, I created this data set age info. I got the resid, I'm taking the absolute value of the residual. Again, remember the residuals are positive, negative. What I'm doing here is I'm doing, in this case, for the simple linear regression, I'm doing a correlation of the absolute value of the residual and the predictor. If you have a multiple regression, it would be the absolute value of the correlation, absolute value of the residual with the predicted value. When I look at this correlation, see what's going on. The correlation is highly significantly positive. So this means on average, as my age increases, the absolute value of the residuals increase. That's funneling out, right? So as my age is on average, as age increase, the absolute value of the residual increase. That's funneling out. If the correlation was negative, significantly negative, that would mean as the age increases, the absolute value of the residual is decreasing. That's funneling in, right? So this little simple derivation, the absolute value of the residual as a function of the predictor in a simple linear regression or the p-hat in a multiple linear regression, that's a simple test to assess violation of homoscedasticity. This is going to be a test that we're going to use down the road. So we'll catch this down the road. But I just want to give you guys that as a little preview. So again, this is our chapter 17, 735 that we just did. I'm going to jump back to the PowerPoint slides. So again, we saw with the non-independence of the error term, look at that residual sequence plot. Do we see any serial correlation that we assess through the Durbin-Watson statistic? With the outliers, kind of look and see what the big residuals are. Again, look at detect any problems as we saw. The important explanatory variable, in regression, you saw look to see if they excluded predictor and the residual as a pattern. The ANOVA model doesn't really apply yet until we get down the road. Again, the normality of the error terms. Again, looking at the plots, better yet, better to assess it through the test of normality. So with this constant of variance, we saw the Levine's test is the default. There are these three other variations. All the other three variations deal with deviations in normality. But like I said before, if the data is deviant from normality, we're not using an ANOVA model. We're not using a general linear model. So again, we should really be using the Levine's. Now, in section 18.4, the book discusses weighted least squares, not a transformation, in the ANOVA model, but weighted least squares to accommodate when you have a violation of heterogeneous variance. So as we move along, there's going to be a couple of times where the book and I go in different directions. The book's great. Like I said to you guys before, it's the book I used in graduate school. Again, having the electronic version of the book really works well. Obviously keep the cost down. The book's great. The book's great, but there's a couple areas the book goes at that I don't exactly go hand in hand with. And the other one is, well, if we have a violation of homogeneity variance, why don't we just model the heterogeneous model instead? And the heterogeneous analysis variance model will allow the variances to be unequal across the groups. Now, some of you guys may say, why don't we just do that from the start? Well, everything with model building you guys saw in 5.12 is we're trying to fit the parsimonious model. So unless we have a need to fit unequal variances, We're not going to sacrifice more parameters to be estimated. Because again, in the example we just looked at with the Rust inhibitor, we would need 4 separate variances to be estimated instead of 1 pooled variance. So again, we're always trying to work on that parsimony unless we have to step away from it. But I'm going to show you guys this example real quick here, this chapter 18 hetero. So when I go here, the chapter 18 hetero, give you an example here. This one's a real life study. And the one thing with this data set on D2L, you guys are going to see, it's called head ANOVA. It's got a .st2 extension. And in 511, you guys may have heard of different versions of SAS data sets. It's an older data set. It's a SAS version 6 data set. So the ST2 is not a sound file as it may be appearing on your computers, actually an older SAS file. So when I change my libname statement to have that engine, the V6 engine, I'm able to access the database. So I'll go real quick here, show you guys the data real quick. My fault. I gotta get to my new drive on my computer. So again, this computer is a little new. So some of the math type symbols didn't carry over. I got it. Okay, cool. There's my 54 observations. So give you guys a little lay of the land. So this was a treatment study involving 54 individuals. Treatment of depression. I got their treatment condition where they were treated by 1 of 3 treatment arms. It's part of the behavior activation study you guys saw. So in this case here, it's medication, behavior activation, cognitive therapy are the 3 treatment arms. 1's medication, 2's BA, 3's cognitive therapy, I believe. In this case, we're looking at the endpoint Hamilton. So we got 48, 6 of the people dropped out. And in this case, these are 54 initial, 48 completers who have a history of a parent who was involved in a depression trial previously. So like a family history of depression that we're looking at. We're looking to see whether or not the treatments are effective in treating these individuals with a history of depression in the family by one of their parents. Show you guys a little descriptives of the data. So again, remember, lower is better. So here's the medication, the the behavior activation, the cognitive therapy. So if you look real quick, you know, the means look really different across the 3 groups. So it looks like that behavior activation separating from the other 3. The sample sizes aren't the same. The patients, this was not a stratification variable in the randomization. So it's just a variable we observed. Here's the means. Here's the standard deviations, the variances. Now, one thing you guys could see, it's kind of like that first group, the medication is the smallest variance in their response to endpoint depression. Lower is better. It's that last group, which is really big variance, and the middle group is, you know, middle variance as well. Now, to show you a little of the data as we look at some of the graphics. So here's the plot. We look at the plot here. See if I can get to it. Right, so we go right there. You know, we got this plot real quick here. Let me just get out of this really quick. Let's jump out of SAS. Jump back into SAS. Open that guy back up. Put the nums on the right. Let's do what we just did. Okay, here's the plot. I just want to get the plot where everything was visual on the same page. So now, as you guys start looking at it, that's the profile of the plot. So when I look at this, it's kind of like, I don't know. Like you said, it does look like there's some more spread in group 3. Right away, I can't really test whether or not it's a function of the sample size. I think this one had the biggest sample. But it does look like there's a little difference in the spread. You know, so this one a little lower than the other two, a little bigger than the other two. So it looks like there is definitely more spread in group 3. The mean profile is saying something about the mean separation. But if we go here and we ran it, the ANOVA model. Now, we're gonna do the Levine's test, but I want to show you what happens if we do one of the other tests as well. Let's go ahead and run the ANOVA. Now, this is real life data, and this cracked me up when I analyzed this data, like whatever it was 15 years ago. Well, I never, ever, ever saw a p-value that close to the alpha level, right? So the first time I ran this data, I was like, oh my God, I go, this is pretty cool. And so immediately I thought about bringing it into the classroom, and obviously it's here in front of you guys, as you guys can see. Real data, real R-squares, not the textbook stuff you guys are seeing. But again, if we looked at this, we'd say, okay, based on available data, we have sufficient evidence to indicate the on average mean depression across the 3 levels of treatment are not the same, with at least one separating. If I jump down really quick, you know, with the LS means, we can see, okay, the thing that's really driving the effect is we see we see a significant difference between treatment 2 and treatment 3. So on average, we say that treatment 2 is statistically superior to treatment 3 in the treatment of depression amongst these individuals with family history of depression. So we end up seeing that there. So that's pretty cool. A trend for 1 versus 2, you know, that 0.069 p-value. So we see that. But now, if you guys were paying attention when I jumped, right, so there's the visuals, but here's the Levine's test. So based on the available data, we have sufficient evidence in our data to indicate that the variance across the 3 treatments is not the same. We have a violation of homogeneity variance. So any inference based on this output is wrong. It's wrong, right? Because again, this is the output for a model that assumes equal variance across the 3 groups. So this whole p-value, we can't interpret it. This p-value is wrong because our data violates the homogeneity of variance assumption. So we end up getting that there. So that's that violation of homogeneity of variance. So, and then here's the Brown's foresight. So you'll see it will change. The p-value will change. I would use the Levine's. Brown's foresight is making this variation due to deviations from normality. We don't have any evidence of violation of normality. But again, but don't play the p-value game, because the p-value will change depending on the technique you use. We will use Levine's test. Okay, that's cool. That's cool. Some people may want to know what's driving the variances being unequal. You know, you can use proc t-test with some of the where command, because you guys remember with the proc t-test, there is this part right here with the equality of variance test. So it's comparing group 1 to group 2. So in this case, just looking at those two, not a significant difference in variance. 1 to 3. The big thing to realize about this, we're not doing this for any kind of statistical true test. So we see in this case, it looks like when we compare group 1 and group 3 excluding group 2, we have a trend towards significance. The group 1's variance is marginally smaller than group 3. But realize we're not using the whole sample, the whole data set. This is just helping us tell the story that we can say we see overall a violation of homogeneity variance. When we focus on pairwise subgroups of the analysis, group 1 and group 3 are showing a trend towards significant difference variance between each other. And then this is 2 and 3, which is going to be non-significant. But again, this is not necessary for this t-test subgroup. Is not necessary for statistical assessment, but part of the story. So again, with that group 1 and group 3, from a subgroup analysis of group 1 and group 3, we see a marginal difference of unequal variance between the two groups. Okay, so we just ran that, right? So in this case here, sure, I'm just going to change one part of the output right there. So we got this, so that's cool. So we just ran that, so we just ran the model, and we see what's going on. So again, with the big punchline, we know this p-value is flawed because of the violation of homogeneity of variance. How we fit unequal variance in SAS is I'm going to introduce you to this procedure we're going to see in chapter 25 and 27 called proc mixed. Proc mixed is going to fit the heterogeneous variance model for us. Proc mix, data equal 1, data set you're analyzing. COV test is an option. It's going to produce the variance test for us, basically the variance matrix. Like proc GLM, the categorical predictors in our class statement, the model statement will give us the model just like proc GLM. The one thing different from GLM compared to proc mix, instead of solution, S will give us the regression coefficients. Instead of the output line to get the outputted residuals and predicted value, this out PM in the model statement will give us the predicted values and the residuals from the model. Now, how we tell SAS to fit the heterogeneous ANOVA model, it's this line right there, line 122. We tell SAS repeated slash group equals TX con A. We're telling SAS we want separate variances estimated for each level of treatment. The treatment variable in this case is TX con. The R is an option. It's going to have SAS print out the variance, the variance estimates for us. So again, you don't really need to worry about that R. I just put in there to show you part of the output that we're going to see in chapter 25. But it's really this, repeated. You're telling SAS you want to repeat the estimate of the variance, but not the pool variance, the variance estimated separately for each level of treatment condition. In proc mix, the LS mean statement works exactly like GLM, where we could do TDIF, PDIF, and then we could also do adjust equal Tukey, adjust equal bond, adjust equal Chevet. Proc mix does not have a mean statement. It only has an LS mean statement, which is why I lean on the LS mean statement mostly. But check this out. When I go here and I run this, here comes the output. Proc mix output looks just like this. With the COV test, SAS is estimating three separate variances for each of the 3 levels of treatment. So person 1 is in treatment 1, which is their variance. Here are the regression coefficients. just like we saw in Proc GLM, but this is what we need. This is the overall ANOVA assessment, the equality of the three group means. This is the equality of the three group means in a heterogeneous ANOVA model. And look at this. So based on the available data, we do not have sufficient evidence to indicate a significant on average difference across the three levels of treatment. Fitting the homogeneous ANOVA model, we had a p-value 0.0499. Fitting a heterogeneous ANOVA model, it's now no longer significant. Now, there's been a lot of attention on people, focusing on p-values. But right now, that's kind of our typical go-to platform. The alpha line is drawn. If it's below, it's significant, right? If it's at or above, it's not significant. So again, when we model the data, rather than throwing the data in the model, we see a difference. And this is why I ran this data about 15 years ago. I thought this was really cool for you guys to expose you guys to a situation where if you're not paying attention to the assumptions, you're telling a different story than actually what's truly being seen in the data. And namely, by not accommodating that violation of homogeneity of variance, you're falsely interpreting the model. LS means, Yellows means, this is showing you, the unadjusted p-values versus the adjusted p-values. Now, it's pretty cool, I think, because in Proc Mix, it gives you the unadjusted confidence interval followed by the adjusted confidence interval, which is pretty cool to see how the adjustment impacts it with the Tukey Kramer, since we have unequal cell size. So I think that's pretty cool, that approach, to kind of get a sense of it, of what's going on. So that's kind of cool as you guys see what's going on. As we start building things up, as we start going down the road a little further. So again, keep this in mind as we start moving ahead, as we start moving forward. So let me just go ahead and save this. And I think we're good with this head ANOVA model. So again, we're doing a lot of cool stuff in this one. So again, that violation of constancy of variant. Well, when we go to need a transformation to the outcome, in 512, you would talk about this constancy of error variance. Homogeneity of variance, we've attacked that just now with fitting a heterogeneous ANOVA model. Transformations are really going to help us when we're dealing with normality of the error. The book lays out this idea of, okay, well, if you look at the variance in a relationship to the mean, if the variance is proportional mean, the book suggests a square root transformation. If the standard deviation is proportional to mean, the book suggests a log transformation. Which base really doesn't matter. The two common bases are log base A, the natural log, or log base 10, which are mathematically proportional. The standard deviation proportional and mean squared use the inverse or the reciprocal, and the response to the proportion use the double arc sine conversion. In this case here, these are rules of thumb. And what, so again, the book says, calculate these statistics, take a look at it, and see what you have. In chapter 18, 791, the book walks through this, and namely, in this case here, you're looking to try to see which one has a constant ratio, pretty similar ratio as a function of the variance by mean, standard deviation by mean, standard deviation by mean squared. And in this case here, this one looks pretty close to 1 across the board. So using the book, this would say use the standard deviation by means proportional across the level, use the log transformation. That again is a rule of thumb. what we could do is we could expose you guys to these things called the box-Cox procedures. These are sometimes called the power transformations. And so what SAS does, it tries to find the optimal power transformation for our outcome, looking at the value lambda. And it tries to find this power. When the lambda is equal to 0, it represents the log normal, log transformation. And when lambda is equal to 1, it represents the normal. So no transformations needed. So what we're going to do is we're going to see this through proc transreg. So let me pull up chapter 18, 791 and walk you guys through how we do the box-Cox in SAS. So I'm going to go here, open 18, 791. So we got 3 locations. We got 5 units per location. We're looking at failure time. So I'm going to go ahead and load this data. When I load this data, I can go ahead and run this data out, right? Just run the ANOVA model. So when I run the ANOVA model, as we slide across, not a significant effect overall. Again, you could see something's going on here, especially with these outliers. Surprisingly, not a violation of homogeneity of variance. Again, we only have 5 observations per cell. But when I go and look at the residuals as a function of the G-plot, we start looking at, okay, it looks like something's going on with the residuals. And namely, I'm beginning to wonder, okay, maybe this outlier or whatever. So we start looking at these. And in this case here, well, so that's the little preview. This walks you through what the book would want you to do. As they start moving forward. So now, as I start moving forward, I'm going to go ahead and kick out the residuals, the predicted value, the standardized residuals, the jackknife residuals. Now, first thing, let's assess the normality of the residuals. And as you guys see right there, we see a highly significant effect indicating the residuals significantly deviate in normality. Now, any of the 4 techniques you do, we have a significant difference in normality of the residuals. So we have a violation normality. If we use the book's approach, right? So again, I'm looking at the summary of the data as we go across and go to the top. So location 1, just looking at really some of the information between the data, the median. As we start looking at the residuals, location 2, it's really location 2 where we see the violation of normality is really dramatic. And then when we go to location 3, again, also issues with normality of the residuals. So location 2 and location 3 really show a problem with the residuals. As we start looking at this, so we got this. So if you start using some of the transformations the book talked about, you have to start looking at, in this case here, we're going to transform the outcome. Now, our predictor is a category, so we're not going to transform that. We're going to transform the outcome. So as you guys see on line 118, I'm invoking the log transformation. One thing to keep in mind with the transformations is whatever transformation you use, got to make sure it fits your data. You cannot take the log of negative numbers or the log of 0. So if I have a 0, I may consider shifting the outcome. So line 119 showing you when I shift the outcome by 1 rather, to accommodate the 0 value. Some people use different shifts. Now, anyway, anytime you have a 0, you have to bump it from 0. Some people use 0.01, 0.05, 0.1. I like the 1 because the 1 is 0 is mapped to 0. The log of 1, 0. So that's just something to keep in mind, right? So now I invoke the log transformation. And the reason I invoked the log transformation is I didn't do it here, but if I looked at what we did there by looking at the ratio of the standard deviation by mean being relatively constant across the 3 locations, this suggests the log transformation by the rule of thumb from the book. And when I do that and fit this model, okay, so when I fit the log transformation, not significant, but based on available data, we do not have sufficient evidence to indicate that the average failure time is significantly different across the 3 levels of location. You know, if your alpha was 0.10, it would be significant in that case. No issues with respect to Levine's test, the violation. You look at standard deviations, you know, they're pretty close, and it's not surprisingly. But now if we looked at the normality of the residuals, we can see now, wow, you know, no evidence, well, that's the jackknife, no evidence of a violation of normality of the residuals. So the transformation did correct the violation of normality of the residuals. But again, that was following, you know, the book's rule of thumb as we moved on. Even if we look within cell, you know, so this is location 3, no evidence. And this is location 2, no evidence of deviation normality. Then location 1. So wow, that really did correct the issues of normality as we moved along. Again, get some of the plots. Some of the goodness of fit plots we just run across quickly. Some of the ones you may be interested in. Again, this one's not transformed, but I think when we look at this normal probability plot, if we're doing it manually that way, you could definitely say that's not a line. As we move forward, I want to drop down towards, well, actually, let's take a look at the autocorrelation. So we're doing this by location. Brand 1, or location 1, location 2, location 3. We assess autocorrelation as a function of location. I'll go to the top. Here comes location 1. Autocorrelation not significant. Autocorrelation not significant. Autocorrelation not significant. All right, so in analyzing data originally, we have no issues with respect to homogeneity variance, no issues with respect to independence, but we have an issue with respect to normality of the residuals. And you can look at some of the locations. This portion of the code showing you where we generate the output in the slides. All right, so there's the output of the slides. You guys saw with the ratio of the standard deviation by mean. Again, you're looking to see which one yields a near similar result as the rule of thumb. But I think it's more better to use proc trans reg rather than eyeballing those ratios. Go and load the data again. Now with trans reg, to use trans reg to fit the box Cox, trans reg doesn't have a class statement, So I'm creating two dummies right there. Line 438 and 439. These guys will give you 0, 1 indicators as we move forward. So these are what we call truth. If the thing inside the parentheses is true, give the variable a 1. If it's false, give it a 0. So using 438 and 439, when you guys see this, you see location 1, location 2. So I got my two dummies. When I fit this, I'm going to go proc transreg, box cox for the model, then identity local 1, local 2. So again, think of this. This is my predictor. Inside the identity function, what do I want to assess the box cox on? My y. When I run this proc transreg, in this one here, SAS is telling me the optimal transformation is lambda equal to 0. That means raise the outcome to the 0 power. In the slides, whenever you see 0, it means use the log transformation. And we're going to use the natural log. Because the natural log, like you guys are going to see in 507, links to odds ratios. When lambda is equal to 1, it indicates no need for a transformation. So when we go here, that's telling us use the log transformation. We didn't have to create all those ratios. So SAS is saying based on the box cox, a log transformation is needed to normalize the residuals. In this one, I'm throwing in line 474 as a row of data. So line 474 has 0 as time. When this is in my data set, I'm doing the same code. When this is in my data set, watch what happens here. SAS is telling me one of the values encountered is wrong. Well, invalid. In this case, the box cox, one of the transformations it wants to use is the log. So anytime you have 0 or negative values, you'll get this warning. So in the log, it could, if your data is really thick and you didn't look, this will give you a sense of, now I got negative or 0 values. If you got negative or 0 values, you need to invoke a shift, which I'm shifting the data by 1 here on line 492. And then I'm running the box cox on the shifted transformation, which tells me, okay, in this data, the optimal box cox transformation is raising the outcome to the 0.25 power. The 0.25 power means the 4th root, not one of your more common roots like the square root or even the cube root, but raising it to the 4th root. This is the one that most normalizes the residuals. In this case, I'm going to show you guys this. PBO extends the output we just saw and creates a block output. So it prints the block output for various lambdas. So when I do this and I look above, you'll see this table here, right? And when you guys see this table here, there's a couple of symbols, the star, the less than, and the plus. The less than is the best lambda. The one that optimizes the fit and normality of the residuals, that's the 0.25. That's what we saw in the output. The star and the star gives a 95% confidence interval range, which again you can see is the 0. But what's most important is this thing called the convenient lambda. And what the convenient lambda is saying is, you know what? We realize the box cox transformation may not be the most usual transformation. And so what the convenient lambda is saying is, you're not really having a significant loss of fit by using the lambda 0. That's the convenient lambda. So there's not a significant degrade in fit. The fit's still adequate in this case, but you may find the zero transformation a more typical transformation. And for us, when lambda is zero, it means we're using the log transformation. So namely, in this case here, even though the optimal lambda is to 0.25, SAS is saying there is no deficiency in fit when using the log transformation to normalize the residuals. So I would use the log transformation. Why? Again, the convenient lambda is, with a lot of the people we're dealing with, they're not statisticians. That's us. It's our job. Even if they're not sophisticated and statistically, some of them are aware of transformations. The log transformation is something they may have seen somewhere along in their training. The fourth root transformation, not necessarily. Now you're going to say, I have fourth rooted the outcome. You have fourth rooted what? You know, some people may not be able to comprehend what a fourth root is. This one, it's saying not a significant degraded fit if you use the log transformation, which again, we could proceed with the log transformation. So once we get to this log transformation via the box Cox, now our analysis focuses on analyzing this. So we go through all the goodness of it, the interpretations on this. The big thing is realize all these are on the log transform scale. So again, the average failure time, you know, the average for location 1 is 3.4 log units. Not units, 3.4 log units. It's one problem with the transformations. Again, to show you guys, if you do some, you know, if we tried the square root transformation, we may look at that to see how that behaves. You know, with the square root transformation, still didn't normalize the residuals with the Shapiro-Wilks. With the square root transformation, this is a good illustration of. You may get different inferences depending on what technique you use in the normality test. The big thing about this is make sure your normality test is a priori. A priori, I will use I'll use Shapiro-Wilks. In this case, you know, if you play the p-value game after the fact, that's wrong. It's kind of cheating, like we said. But realize different approaches can give different outputs. The Komorov-Smirnov would say no evidence in significant deviation normality, whereas the Shapiro-Wilks does. You know, so again, that's part of this illustration that you guys see here. We go back to the log time that we're invoking. Like we said, everything's on the transform scale. On line 583, I'm going to output the Ellis means and the confidence limits here using that ODS output. So again, here's the means with the confidence bounds. These are all on the log scale. Whenever you're dealing with transformed outcomes, you may want to back transform them, undo the transformation based on the model-based estimates. So line 599 to 602, I'm back transforming the estimated means. So for the Ellis means, we logged them. To undo it, I'm exponentiating them, which I'm doing on line 601. So in line 601, this is giving me the back transformed means. So again, I can see real quick here, okay, so on average, model-based estimated for the average failure time for location 1 is 30.35 on the original units, 9.94 on the original units for location 2, 84.49 on the original units for location 3. We may want to even do that for the confidence intervals. So the back transform means are really the things you should be talking to the investigator about. One thing to keep in mind, the model will yield symmetric confidence intervals. And what I mean by symmetric, the difference between these two values is exactly the same as the difference between these two values. With transformations, that's not the case, right? This is the lower bound. The difference between the lower bound and the upper bound is about 60 units. With the transform 279 to 84, it's about 190 units. So, you know, the estimates on the transformed outcome, confidence interval wise, will be symmetric around the estimated means. But when we undo the transformation, things are no longer symmetric. So that's pretty cool. That's pretty cool stuff as we start moving forward with that. But again, you know, when we're doing the transformation, once we get the transformed outcome, we got to go through the same steps of goodness of fit. The big thing is when we're fixing one thing, we hope we don't break something else. So again, if you fix normality, you may end up getting a violation HOV, right? So, you know, autocorrelation's not going to be, yeah, that's there regardless if it's there or not. Transformation of the predictor in the regression model, you may have done this, you know, probably more for lack of linearity of the relationship. But independence of the error term, I wouldn't really, again, another point with me in the book, you know, disagree with. You know, if your data is that, you know, it's kind of hiding the autocorrelation when you're transform the predictor. The big thing you may see, lack of normality, but in reality, what we're doing with the ANOVA model saying, we're not going to transform the predictor. It's a category. So we're not going to transform. If there's issues with the data where you cannot fix them, you know, a lot of people go to non-parametrics. Now, if you have violation independence of the data, non-parametrics is not going to fix that. No, it's just when the data cannot be normalized or whatever, you know, there's something really wrong with the data. Some people go to non-parametric test, which again, you can see the handout on D2L, which lays out the different non-parametric tests in SAS. The non-parametric analog for analysis of variance is this thing called the Kruskal-Wallis test. And for analyzing 3 or more independent groups, if it's 2 groups, it's called the Wilcoxon rank sum test. You know, in this case here, the Kruskal-Wallis test, the null is the samples come from identical distributed populations. The alternative is samples come from different. Now, it's kind of a test of equality of medians or modes or central tendency. So the test statistics H. So in this case here, we're looking whether or not it's significant. So I'll just give you guys this little quick preview of non-parametrics. It's a course of its own, but I figure I'll show this to you guys really quick to wrap up this topic. So I'm loading this one here, days treatment ID. And what you guys can see here is treatment 3, I'm looking at backwards. Treatment 2, treatment 1, no evidence in issues with respect to normality. Again, if we ran this data as a GLM, highly significant difference on average. And you can see it's really treatment 2 that is the longest time. But if we wanted to run it non-parametric, this is the command. Non-parametric, one way we'll do the Kruskal-Wallis test. There is the categorical predictor, the variable we're analyzing. Oh, it's almost like proc-t test. You guys saw that in 512. Then I quit this. So with the non-parametric, gives you a lot of output. I'll go to the top of the output and then we'll walk our way down. That's the GLM. that we just saw. Here comes the non-parametric. Giving us the means. This box you guys see right here, same box as the ANOVA box. This is run the ANOVA model right there. See the 150.84? That's the 150.84 in the ANOVA box. So the first part of the non-parametric output is the ANOVA model. And even the ANOVA box plot. This is where we start doing the Kruskal-Wallis test. So the Kruskal-Wallis test is right here. So the non-parametric test is based on available data. We see significant difference on average across the 3 cells, across the 3 forms of treatment, indicating that the 3 treatments are not coming from the same population. They are significantly different populations. And that is the non-parametric analog of the one-way ANOVA model. So again, that's the output for the Kruskal-Wallis. Whole bunch of different variations, as you guys would see down below, that kind of like the Levine's test, the p-values will change, but they usually should be in the same kind of vicinity. There's van der Waerden, Savage, Komor-Smirnov right there, and then the Kramer-von Miss. So again, but for us, the Kruskal-Wallis is right there at the really the second portion of the output. The first portion of the output is the ANOVA, which is pretty good because again, you can see highly significant fitting the ANOVA model, fitting the non-parametric model, still significant, but not as dramatically. So that wraps up chapter 18 and what I call part 1 of the course. So what you guys are going to see is next, we go to chapter 19, so part 1, video 6, where we start, like what we did here, we start blowing up the 2-way ANOVA model. So again, look forward to seeing you guys in the next video. Thank you for your participation, your attendance, and I'll see you at the next one. Thank you.